Okay, so in this lesson, we're going to review some trig stuff that you covered in Algebra 2 and maybe the year before as well, and maybe introduce some new things depending on how much you guys got through last year. The reason we're doing this in pre-calc, though, is so we can study new types of functions. So we're going to study what are called periodic functions. So this is the graph of sine of x, and notice it makes this cool wave shape, right? So these types of functions are used to model things that kind of oscillate around an average like this, like the temperature throughout the year. In physics, they model like springs, stuff like that. In computer science, these types of functions are used for data compression in a really interesting way. They also model sound waves. So notice it's a really different shape, and the reason it's such a different shape is the algebra of this behaves quite a bit differently than the algebra of something like a polynomial. So our goal here is to get really comfortable with that algebra so that when we move on to study those functions, we're masters of that already. To do that, we're going to consider a problem involving some of my favorite buildings in Chicago. So I picked these because I think they look cool. These are the Marina Towers downtown. And I also picked them because we have two of the same building. There are two towers side by side, and this is going to illustrate my point really well. So what we're asked to do is imagine we're looking straight up at the tower. So here we are on State and Wacker Drive in scenic downtown Chicago. So I'm asked to look kind of straight up at the tower. So here I am looking at the first tower. And the question is, if I turn to look at the other tower, what can we infer about the angle at which I'll lift my head, right? So imagine you're standing here. Oops. Oh God, what have I done? I just accidentally clicked on Lower Wacker Drive, I think. There we go. So imagine we're standing here on State and Wacker. The angle that I lift my head, craning my neck back to look at one tower, would be the exact same angle that I have to lift my head to look at a different tower. Whereas if I pick the taller building, let's not use that one. If I pick the taller building, I'd have to lift my head even higher to look at it, right? So this is kind of common sense. But it's really the key to all of this, right? Is that if I have this angle, we'll call it theta, that's a little circle with a line through it, it's going to be related to the length of this side, right? And if I have the same side length with my second building, that angle would have to be the same. So the answer to my question is the angle would be the same since the length of the opposite side is the same. Now notice we don't have enough information to figure out the height of that tower yet. We are just given that 62.4 degrees. But in question 2, we're given another piece of key information. That's the length of the bridge is 307 feet. We're asked to estimate the height of the towers. So here's where we use our SOHCAHTOA, and I gave you this down on the bottom, but you're familiar with this. We have, I always like to label my sides. We have opposite and adjacent, and the hypotenuse is not given, right? So my equation is going to be, if I have opposite and adjacent as the relationship I'm using, I'm going to say tangent of my angle is equal to opposite, which is x, over 307. And then I can solve it. This is just a number, 307. If I multiply times that on both sides, I get 307 times tangent of 62.4 degrees is equal to x. And then on my calculator, this is the last time we're ever going to use degrees on our calculator in here, so let's make sure we're in the correct mode. I'm going to hit mode, and then make sure I'm on degrees. This is kind of like feet and inches. And I'm going to type in exactly what I got. So 307 tangent of 62.4. And there's my answer, 587.2 feet. And you can make a note that that's from my calculator if that's helpful to you. Okay, so once we know a side and an angle, we can use that to solve a right triangle. Then the last question, again, is obvious. Suppose we shrunk both the tower and the bridge down to half their size. So imagine we drew a smaller version. So this would be, I don't know, 153 feet, and this would be about 293 feet. This angle would still be 62.4. So the answer here is it would be the same since we didn't change the relationship between the sides of the triangles. Okay, so here we have an example of how to solve a triangle using a trig equation, and some examples of sort of the logic we're using here. So my key takeaways here is first that the measure of the angle in a right triangle is related to the side length of its opposite side. So how high I lift my head is related to the height of the building, right? The second is all I need to know is an angle and a side of a right triangle, and I can get all the rest of the measures I need just by SOHCAHTOA algebra. And then the last thing here, question number 3, is that scaling a triangle up or down does not change the angles. Okay, so on the next page, we're going to consider 3 more relationships. There's actually 6 trig ratios altogether, and we're going to consider how to use one to find another. Okay, so here we have all of our trig ratios, and then these 3 other ones are probably the 3 you're less familiar with. These are called the reciprocal trig ratios. And the reason they're called that is they're just our original ones flipped. So notice cotangent is adjacent over opposite. It's just the opposite, the reciprocal of tangent, right? Cosine, adjacent over hypotenuse, has secant as its reciprocal. And yes, that is confusing, thanks to Greeks. Sine, opposite over hypotenuse, goes with cosecant. Okay? And notice these all involve the same angles. So if I'm given one, if I know that cosine of A is 3 over root 58, I can find all of the other ones. And the way I would do that is just I would draw a right triangle. I would pick some side A. If cosine of A is adjacent over hypotenuse, well, that would be 3 and then square root 58. I can figure out my other side by being like a squared plus 3 squared equals square root of 58 squared. And then a squared plus 9 equals 58. That gives me a squared equals 49. And a equals 7. Right, so just Pythagorean theorem to get that remaining side. And cotangent of A, well, this is adjacent over opposite, which is equal to 3 over 7. And then sine A is opposite over hypotenuse, which I'm just, again, getting from my table. And that's 7 over the square root of 58. However, I don't like having my square root in the bottom, so I'm going to multiply by a funny form of 1. I'm going to say square root of 58 over square root of 58. And I'm going to leave it like this. 7 square root of 58 over 58. This is called rationalizing our answer. Okay. So notice, if I really wanted to, using my little table here, I could find all 6 of these, just given 1. So it goes back to this idea of once I know 2 parts of a right triangle, I can solve the entire triangle.